Now we're going to find the Laplace transform of the sine of k times t. This is equal to the integral from 0 to infinity of e to the negative st times the sine of kt dt. That's right, we are going to integrate the product of an exponential with a sine function. We are going to use integration by parts, and you may remember that after 2 steps, we're going to repeat this expression in the integrand. I'll take us through this somewhat quickly, but because I know what's going to happen when we integrate such a function here, I'm going to say that that integral is I. It doesn't matter which one between the exponential and the sine function, which we let be u and which is dv. So I'll just let u equal the sine of kt and dv equal the e to the negative st dt. Then du is k times the cosine of kt dt, and v is negative 1 over s e to the negative st. The integral then, the Laplace transform, is negative sine of kt over s times e to the st evaluated from 0 to infinity plus k over s times the integral from 0 to infinity of e to the negative st times the cosine of kt dt. This time I'll say that u is k over s times the cosine of kt, so that du is negative k squared over s times the sine of kt dt, and then dv is still going to be e to the negative st dt, so v is negative 1 over s e to the negative st. Now, just evaluating negative sine kt over s e to the st from 0 to infinity, we can see if we put infinity in place of t in the sine function, it's always between negative 1 and 1, but 0 in place of t in the e to the st in the denominator makes that whole thing go to 0. Putting 0 in place of t in the numerator, hey, that's the sine of 0, so that thing's 0. So the whole first term is going to go to 0. As for the rest of it, our integral is now negative k over s squared e to the negative st times the cosine of kt evaluated from 0 to infinity minus k squared over s squared times the integral from 0 to infinity of e to the negative st times the sine of kt dt. You might recognize that last bit as negative k squared over s squared times I. Before I change that, though, I want to evaluate this negative k over s squared e to the negative st cosine of kt from 0 to infinity. As before, infinity in place of t, since this is e to the negative st, is going to give us a 0. The cosine function is between negative 1 and 1 after all. Substituting 0 in place of t, though, into the cosine of kt is going to give us a factor of 1. 0 into the exponent of e to the negative st is going to give us another factor of 1. We are subtracting the evaluation at the lower limit. So I'm going to rewrite, we've got I is equal to, that k over s goes, or k over s squared goes positive. Then I have minus k squared over s squared times I, because the original integral reappeared. We want to solve for I, so I'm going to get them on the same side, and then I'll factor out the I. The result is going to be 1 plus k squared over s squared times I is equal to k over s squared. Getting common denominators inside the parentheses on the left results in s squared plus k squared over s squared times I is equal to k over s squared. S squareds divide out, and we get that the integral is equal to k over s squared plus k squared. All right, that gives us another formula. The Laplace transform of the sine of kt is equal to k over s squared plus k squared. Again, we started with a function of t. Now we have a function of s. We could go on like this, but frankly, I'm not going to do it. I encourage you to test some of these formulas out. The Laplace transform of 1 is 1 over s. We figured that out. The Laplace transform of t was 1 over s squared, but that generalizes to t to the n. Gives us n factorial over s sub s to the n plus 1 in the denominator, for n being a positive whole number. We computed the Laplace transform of the sine of kt, giving us k over s squared plus k squared. The Laplace transform of the cosine of kt looks like the denominator is the same, but the numerator has an s, so it's s over s squared plus k squared. E to the at transforms to 1 over s minus a. Notice that whatever the a is in the exponent on the t side, it's negative a there. There's a sign change. And then if the denominator looks like the result of a transform of a sine or a cosine, but it has a minus, then we can connect that to the hyperbolic sine of kt or the hyperbolic cosine of kt with, again, k in the numerator for the hyperbolic sine and s in the numerator for the hyperbolic cosine. You're going to get to know these whether you really work on memorizing them or not, but I'd say work on memorizing them.